whoops. Okay, so this one says, let f be a function defined by that piecewise function. For what values of k and p will f be continuous and differentiable? Okay, let me get this real quick. Okay, so we want this function to be, first we'll focus on making it continuous. Okay, so in order for it to be continuous, each of these pieces has to equal the other when x equals 1. So we'll plug in 1 to each of them and set them equal to each other. Okay. So left-hand side is just 1. Get that. So you can see k plus p has to be 0. Okay, and then, so this is f. We can also find f prime. Take the derivative. So derivative of the top is 2 minus 2x for x less than 1, and then 2x plus k, because the p goes away, for x greater than 1. Okay, and then we'll do the same thing. So we'll plug in 1 to the top, and you get 0. Plug in 1 into the bottom, you get 2 plus k. So you get k equals negative 2. And then if k plus p equals 0, and k is negative 2, that means p has to be positive 2. That's it. Okay, let f be the function defined by f of x equals 2x e to the negative x for all real numbers x. Okay, so they say find the x-coordinate of each critical point of f. For each such x, determine whether f is a relative maximum, relative minimum, or neither. Okay, so first we'll find critical points, so we have to see where this is undefined and where this is equal to 0, the derivative. So here, sorry, we'll first take derivative. And actually, I'm going to rewrite this. Okay, then we'll take derivative. Okay, derivative of the top, 2 times the bottom, minus the top, times derivative of the bottom, all over bottom squared will be like that. Okay, and then we can, really we can like factor out an e to the x from the top. Actually, I'll kind of write it over here. Actually, I'm going to factor out a 2 e to the x, and we're left with 1 minus x. Okay, and then you could see like this is e to the x will cancel out with, this is e to the x. There's 2 e to the x's here, so one of them will cancel. So it'll be like that cancels out with one of those e to the x's. This will be 2 times 1 minus x over x. Okay, this is never undefined because it's never, the bottom is never 0. Exponentials can never be equal to 0. So the only critical point comes from when really the whole fraction equals 0, but fractions equal 0 when the top equals 0. And so the only critical point is x equals 1, because that makes the top 0. Okay, find the x-coordinate of each critical point. Okay, so we did that. Okay, determine if this is a relative maximum or neither. Okay. put that on a number line. And then we go back up to the derivative here and then do test points. So if you plug in, so maybe I'll make 0 a test point and then 2 a test point. If you plug in 0, that's positive. Plug in 2, that's negative. And so remember, positive means it's increasing, negative means it's decreasing. So this has to be a relative max. Okay, and that's it. Okay, this one says that particle x moves along the positive x-axis so that its position at time t is greater than 0 is given by that function. Is particle x moving towards the left or towards the right at time t equals 1? Give a reason for your answer. Okay, so things are moving to the left when the velocity is negative. And then the derivative of position is velocity. So here I'm going to rewrite this position function. Okay, and then velocity is derivative of position, which is 15t squared is 18t. Okay, and then now we're only interested in to see if what's happening when t equals 1. So we'll plug in 1 into this. And this is -3. Okay, so that means since the velocity is negative, the particle is moving to the left. That's it. All right, this one says, gives you a function defined on a closed interval from -5 to 4. The graph of f consists of 3 line segments, so those 3, and is shown in the figure above. Okay, and then they give you a function g, and they define it in terms of a definite integral of f. Okay, and then they say on what open intervals contained in from -5 to 4 is g of x both increasing and concave down. Okay, so increasing means we want to know if g is where g is increasing, so we want to know where g prime is positive. And then concave down means the g double prime is negative. So we want to figure out where g prime is positive and at the same time g double prime is negative. All right, so we need to get, the first derivative. So we'll take derivative of this here. Okay. Oops. Okay, so now we take derivative. And remember, if you're taking derivative of an integral, and the bottom's a constant and the top is just x, then all you do is plug in x into the whatever function is here, just replace it with x. It's, now it's in terms of t, so just replace that. Any variables that you see here, replace them with that top variable. Okay, so g prime of x is just f of x. So keep in mind what what we wanted to do. We wanted to figure out where g prime of x was positive, so we'll figure out where f is positive, since that is g prime of x. So we look, f is positive from -5 to 2. Right, all this above the x-axis from -5 to 2. Okay, and then now let's take second derivative. And we can see that's just the first derivative of f. Okay, so now we want to think about where the second derivative is negative, but that's just where f prime is negative. So this function's derivative is going to be negative when this function is decreasing. So this is decreasing from -5 to -3, and then from 0 to 2. Okay, and we want to find the intersection of both of these. And so you can see this, the intersection of these is just this. It's just -5 to -3, and then 0 to 2. And just to see clearly why that is, think about if you, this is just to explain it, you wouldn't do this for sure. Let's put all this stuff on here, -5, -3, 0, and 2. Okay, so think about this first interval is -5 to 2. So that goes from here all the way here. That's all these numbers. And then this one up here is -5 to -3, and then 0 to 2. Okay, and then you can now see, like, they have in common this little section and that little section. That's -5 to -3, and this is 0 to 2. Okay, and then that's going to be the final answer. So -5 to -3 union 0 to 2. Okay, so this is the last one, has to do with differential equations. Okay, the axes provided sketch a slope field for the given differential equation at the 9 points indicated. Okay, so look at the points indicated. So it's all the points that have either 1, 2, or 3 as the x or y coordinate. Okay, you could probably, a lot of people would probably do this in their head. I'm going to make a chart just so we can see clearly. Okay, and then we'll put okay, so we got every combination of x is 1 and x is 1, 2, or 3, and y is 1, 2, or 3. All right, so now, and then this up here, this will be our dy dx. And for this problem, it's 2 minus y over x. Okay, so what this is saying is, for any given ordered pair, any value of x and y, you can plug it in here, and what that'll give you is the derivative, which is the slope of the tangent line. So all we're going to be, this column here is all the different slopes that we're going to put, we're going to make little segments of slopes, centered at each one of these lattice points, and then that'll create what's called a slope field. Okay, so let's plug those in. So if you plug, I'm just going to be plugging in each one of these points into here and then recording it in this column. So if you plug in 1 and 1, you get 1. Plug in 1 for x and 2 for y, you get 0. Plug in 1 for x and 3 for y, you get negative 1. Okay, plug in 2 for x and 1 for y. It's 1/2. Plug in 2 for both, you get 0. Plug in 2 for x and 3 for y, you get negative 1/2. Okay, plug in 3 for x and 1 for y, get a third, and a 0, and then negative a third. Whoops. Okay, I'm going to come back here and just, so like at the point 1, 1, we'll draw a line segment that has a slope of 1. So just something like that. 1, 2, 1, 2, we'll draw a line segment that has a slope of 0. It'll look like that. And then at 1, 3, here, make a little line segment that has a slope of negative 1. That. And just estimate. Doesn't have to be perfect. Okay, so now the next 3 points are all when x is 2, and then y will go up from 1, 2, and 3. Okay, so that's here. So we'll start here and go up. Okay, so this line segment is a 1/2, and then 0, and then negative 1/2. Okay, the next one is a 1/3, 0, and negative a 1/3. All right, so something like that. Okay, next one. Let y, for part B, let y equals f of x be the particular solution to the given differential equation with that initial condition. So they're just saying 3, 1 is a point on the particular solution, which is f of x. Okay, write an equation for the line tangent to the graph of f at x equals 3, and then use this equation to approximate the value of 3.5. Okay, so think about how this works. Actually, let me see if I can do this. Yeah, nice. Okay, let me bring this back down here. Okay, so we're given this differential equation, but what this is saying is this is saying the derivative of y with respect to x, so this is really y prime, derivative of some function, is equal to this. So this is the slope of the tangent line at any given point, x, y. So think about if we want the equation for the tangent line, first we need the slope of the tangent line. And so we can do that by just plugging into this. Let me erase this. So we'll just plug into there that ordered pair, 3, 1. So if you plug that in, 2 minus 1 over 3, that's a 1/3. So this is the slope of the tangent line at that point. Okay, and then once you do that, just do point slope form. So with the same point, 3, 1. So we'll do y minus 1 third times x minus 3. Okay, so that's the equation of the tangent line at x equals 3. Okay, then they say use this equation to approximate the value of 3.5. Okay, so now we'll plug in 3.5 for x, and then just start solving. Actually, let me do this. Okay, so that means that y equals 1/3 times 0.5 plus 1, which is a third times 0.5 is a sixth, plus 1 is 7 over 6. That's it. And then maybe just to be explicit, oops, we could say f of 3.5 is about 7 over 6. All right, last one says find the particular solution y equals f of x to the given differential equation with that initial condition. Okay, so now we're actually finding the particular solution. Okay, we're not writing an equation of the tangent line. We're actually finding the particular solution. Okay, so now we will we'll take this. All right. Okay, so now we have to solve this differential equation for y. The way to do that is to separate variables. So we got to get this dy and this 2 minus y have to go on the same side, so we'll divide by 2 minus y. And then this dx and x have to go on the right hand side, so we'll multiply by dx to get that over to the right. Okay, once you do that, then we'll integrate, do an indefinite integral. Okay, so we got that. Okay, so now we have to do two things. After you integrate, you have to solve for y and you have to find c. Doesn't matter what order you do. I think it's easier to find c usually. It'll be easier and it'll be less likely to make a mistake. So let's find c right away by plugging in the point 3, 1 in for x and y and then solving for c. Okay, so I'm plugging in 3, 1 and getting this. Okay, plug in 3, plug in 1, you get ln absolute value of 1, just ln 3. Okay, remember ln of 1 is 0, so this is 0 equals ln 3 plus c, so c is negative ln 3. Okay, so now we'll come back here, we'll plug in negative ln 3 for c. Okay, easiest thing to do, we have options, is to combine these. Okay, and then this will combine, actually I'm going to multiply both sides by a negative first. I want to get rid of this negative, bring it over here. And so, let me do that. So all that does is really switch these. Oops. Okay, now we'll combine these using rules of logs. Okay, so now the right hand side will become ln absolute value of 3 over x. Remember, when you subtract two logs, you do the first one divided by the second one. First argument divided by the second argument. Okay, now we can set these insides equal to each other. Right? If ln of something equals ln of something else, then these inside parts have to equal each other so that the whole thing's equal each other. and then just start solving for y. And then multiply both sides by a negative. And one way to do that is just to switch these around. That's it. That's the particular solution. So just so you know, if you took this 2 minus 3x, 3 over x, and you plugged it in for that y on the left-hand side, which means taking the derivative of this, and then you plugged it in for this y over here, then both sides would be equal. And that's what that particular solution is. Okay, so that's everything.